Sure, Raju, so thank you. Give a hand.
Before we start, remember when Eric gave his presentation, he told us about the physics of saturated gluons, which is encapsulated in so-called colored glass condensate. And the model of gluon distributions in nuclei is called Raju Venugopalan model. Surprise, surprise, we got Raju Venugopalan, who is going to give lectures today on the blackboard, by the way. So you have to rotate in this direction.
Okay, so thank you very much. It's a great pleasure to be here. Thanks to Fred and Alexei for organizing this great school. And I'm sure many of you are either close to being saturated or saturated yourselves. So I decided to give a blackboard talk because I think the pace is more relaxed and can ask me questions as I go along and stop me and ask for clarifications. And if you can't see anything, just let me know. Okay, so I don't give too many blackboard lectures, so it's a bit of a experiment for me, which I'm going to be hopefully doing more of soon. So, okay, so without further ado, I looked at some of the lectures, I want to sort of orient what I'm going to talk a little bit in the context of these lectures that you've been hearing about. And so if I draw the following diagram here, so where I think about probing matter in QCD at finer and finer resolution, and that's going up in Q squared. So I presume by now you all be familiar with the kinematics of deep elastic scattering. So if any of you have any questions about that, just feel free to ask me. And the other axis, I'm going to write X, which is, typically pure K and X, but not exclusively. So this you can think about as a proxy for parton density, which I presume you look at something about from the lectures of Anna Stasto. And so this is energy also. So I can write this. Over X power. So as you go to smaller values of X, you're going to higher energies or higher parton densities. And as you go up in Q squared, you're going to finer resolutions. And so I'm going to draw sort of another line here where I say this is a regime I'm going to call strong coupling. And so that's where typically the QCD coupling is large. So it's something which is of order 1. And it's not clear it's even well defined, this regime here. And then at very large Q squareds, I can say 1, that's asymptotic freedom, and so there will be weak coupling. So when you sit in this corner of this quote-unquote phase diagram, so that's the parton model, right? So parton model, perturbed QCD, jet physics, all the precision machinery of QCD really works here. Okay. But yeah, so the coupling runs as a function of Q squared, and it's very. So now this is a very small region of phase space. So the cross sections are very small in here. So if you think about the total cross section in high energy processes, the region where we understand QCD in terms of some kind of recoupling picture with high precision is a very small region of phase space. So you have to go to very large momentum transfers or very large Q squareds to really compute with confidence. Then there's this region here, which is where lattice QCD works. And when I say works, I mean primarily limited to what I call static quantities. And I'm sure you heard lectures about what that means, that you do the calculations in Euclidean space-time. And so you can only look at ground state properties of the theory, so moments, thermodynamic properties like pressure, and so on. And we can now try to go beyond these regions, and we have effective field theories. So we have effective field theories for specific processes. So for example, this region here for very low momenta processes. So let's say where this is the ion decay constant here. So for such regimes, you can use chiral perturbation theory. It's a highly developed, framework. And if Weinberg is to be believed, it is equivalent to QCD at very low momenta. So it's completely equivalent. So we were to compute the first principles. Yeah.
The pies has to.
Oh, okay. This is F pi. That's pion. So this is 93 MeV. Approximately. So it's a scale of 1 GeV.
Does static quantities mean the same as universal quantities or no?
So static just means that you are so really you're studying the ground state of the system. So you can work in Euclidean space-time. So you're being observables that are really not excited states of the system. So you're right. So you're not studying real-time processes, for example.
Very good. And are we in a large X regime where your two circles are?
Right.
But what do we mean by large X? Like, is there a range?
Yeah. So I don't want to go very specifically in there, but I would say so this. So for example, this regime here, where I talk about the Parton model, it's really derived in something called. So thanks for that question, because there's an asymptotics QCD, which is called Yorkane asymptotics. And that's the regime where, in the language of BIS, your Yorkane is on the order of v squared over the center mass energy squared system. And then these are both taken to be large and held to be fixed. So that's the kinematics that really I'm referring to here. And so of course, it's roughly on the order of 1. Okay, so it's large X kinematics. And I will get more specific as to what I really mean by large X and small x in the context of what we're talking about. But just to stick with effective field theories, there are other effective field theories. When you have something like a large mass in the problem, like you have, charmonium or bromonium, or any quark, light quark systems, so ammonium, where you can also write down theories where you can separate short and large distance scales and compute in some systematic way. Okay, so there's a range of such things that you can do to really understand the full landscape of the strong interactions. But what I'm talking about, it's really a regime that sits here. And that's a regime at small x. And I'll specify more what I mean. So that's the regime, and I'm going to call that high Parton densities as a shorthand. High Parton densities. Yeah, I hope you can see that over there. And so that's an interesting regime where, because the coupling is weak, but the physics is very non-trivial. It's non-perturbative. And the reason is that even though the coupling is very small, so I'm going to call this region the Ray J region. Okay, so this is Ray J asymptotics. So to use the same language here, that's a regime where Q squared is fixed. S is very large, central mass energy squared, but X J in the BIS context goes to 0. Now, just because it's fixed doesn't mean it's small. And one of the great advantages of modern colliders is that we can access the regime where Q squared itself is large. So you're now studying, if you are able to, as perhaps the IC or the LSC, study physics and kinematics where Q squared is large. So you can argue the coupling is weak. You're studying color degrees of freedom. But then you can go to very high energy simultaneously. Then you're starting to probe the regime of these small x's. And so that's, I'm arguing to you, is a very interesting regime because of physics is, even though it's weak coupling, it's highly non-perturbative. And so what I mean by that is that suppose I'm computing some observable, some expectation value of some measure of some object that I measure, the physics of this stuff is not going to depend, as we do in perturbation theory, on some expansion in powers of alpha, right? As you would do in perturbation theory, but fundamentally goes as something which is on the order of 1 over alpha. So this is what I mean by really non-perturbative physics. And this is characteristic of a lot of non-trivial phenomena in this field, like, for example, instantons, right? Instantons are objects which actually satisfy this criteria. And when you apply weak coupling, right, so the coupling is simultaneously weak, then the regime usually corresponds to that of very strong fields. And also, it's classical physics. It's dominated by classical configurations. And I'll sort of try and elaborate. Part of my talk will be elaborating these concepts. So that's why it's very interesting. And okay, so why should we care? Okay, because I think generically, even in QED, we don't understand very strong field physics very well. So an example is the Schwinger mechanism, whereby you produce pairs in very strong fields. And to the best of my knowledge, we really haven't demonstrated that. So we're producing stronger and stronger laser fields. And so the question is, when can you get sort of spontaneous creation of pairs in such strong background fields, and how to compute that in some systematic way? That's a very tough problem and very interesting, and it's driving a lot of experimental effort. Such physics also occurs in the physics of black holes. And ultra cold atoms. And in inflationary dynamics, go to universe. And it turns out that there are certain features of all this physics which may be universal. Okay? So there may be universal aspects of this physics. So in fact, just to give you a sense of that, I'm not just saying words, I'm actually actively writing right now a paper where I'm using some of these ideas to compute gravitational radiation and the collisions of primordial black holes, okay, using the techniques that I'm going to be talking about here. And so, and also there are universalities we have demonstrated with cold atoms and certain features of such strong fields. And inflationary dynamics, actually, there's a very strong connection, which is similar in scope to what I'm going to be talking about. But these are actually concrete universalities here.
Gravitons also self-interact like gluons do, or no?
Yes. Good. That's easy. So there's a radioasymptotics also in gravity. okay, which is comes when you consider the physics of quantum dynamics. And so many of the tricks and techniques that one uses here can also be applicable. So this is kind of the larger context, right? The specific one I'm going to be talking about is that of heavy ion collisions, and that's going to be the subject of my next lecture. And so, in fact, so as many of you heard, the claim that a quark gluon plasma is produced in heavy ion collisions at RIC and the LHC, right? At the highest energies, and I think this is sort of widely believed. So this small matter existed only previously 10 to the minus 5 seconds after the universe was after the Big Bang. And so the question is, can we understand thermalization in heavy ion collisions from first principles? Now, of course, different folks may have different ideas of what first principles means. Okay, but I'm going to argue to you that the answer is okay, and the answer is yes in this very specific radiokinematics, where I'm also looking at the regime where Q squared also gets to be very, very large. And so essentially, I'm looking at alpha S is very small. So ironically, we can show this in the limit where alpha S is 0 in a very particular way, okay? Because remember, as I said, we're also working in the regimes where the fields are very strong. And so assume that I define an occupancy of whatever objects I'm talking about, and they have occupancy 1 over alpha. So this is the regime where alpha S times F is of order 1.
You mean the field of Young-Mills field between two quarks, which are going away from one another, classical field?
Now you'll see what I mean. It's really the regime at small x where you produce a very large number of partons. It's a small region. So okay. So this is kind of the topic of my second talk, but we need to get there, and so I'm going to sort of discuss all of these ideas as I go along. So let's see. Okay, so any questions at this point? All right, okay, good.
So you said we're in the non-perturbative regime as far as alpha S is concerned, but it's definite. Sorry. Let me say this
That's
again.
very important.
Yeah, but I'm looking at this one. It's the bottom left right quadrant of the first board. So
You're talking about here?
no, down one long.
Here?
Yes.
Yeah,
We're in the
exactly. But the coupling is weak,
yes,
right?
exactly.
But the point is that what I mean by non-perturbative, that even though the coupling is very weak, right? What are objects that I'm computing that are of interest to me, which include all of these things here, are objects where the whatever I compute is of the order of 1 over alpha. Okay? And you can never derive a 1 over alpha just by doing a simple expansion of powers of alpha.
I'm trying to map that to an intrinsic charm discussion for why intrinsic charm is non-perturbative, and it's because the gluons are coming off of quark lines and those quarks are bound into a thing. So I'm just wondering, are these objects all either correlated or bound? Is that why it's definitely.
So I don't think it's related, but okay, you can tell me later if you think it is. Okay, so let me just motivate this a little bit further, and then I'll go back to discussing the small x regime. So my talk is really going to be, so as I mentioned, a lot of what you heard about was perturbative QCD from George and Stewart, I gather, and others, right? You heard about the lattice from several speakers, right? That's the regime here. I don't know if you heard about PFTs, something definitely you should think about. And so something like intrinsic charm may fit into this rubric here. And what I'm going to be talking about is the physics of very high particle densities. And I'm going to argue that the physics is very interesting because even though you can compute things in this asymptotic recoupling, the physics is intrinsically non-perturbative. And so there are very non-trivial effects, as you might know from examples in the literature that you may have heard of phenomena that are created, which are highly non-trivial. And I'm going to argue too that many of these can be understood similar asymptotics. And some of the physics may need to be universal, some aspects between some of these different systems in very specific ways. So any questions before I jump in? Okay, so you ask yourself, okay, so let's just start thinking about heavy ion collisions. And so at RIC, for example, at the highest energies, you collide gold on gold ions at 200 GeV for nucleons that are mass. So very high energies. Why is it very high? What do I mean by high? Is that this is much larger than the mass of the proton. So these nuclei, which are moving each with 100 GeV per nucleon, are highly ultra-relativistic. Okay, so they are Lorentz contracted pancakes that are moving at velocities which are on the order of 0.9997 speed of light. Okay. So this is extreme relativity. And at the LHC, so the dominant ions that collide are lead ions, and these are at up to 5.5 GeV per nucleon. So this is, factor of 20 greater energies. And so V over C is a good exercise to see if you can calculate what this is. Okay, so it's extremely relativist. So now if you ask yourself, okay, so we know that at RIC from experiments that we produce on the order of, can someone tell me, or does someone know how many particles you produce in a RIC collision at the highest energies?
It's like 1,000.
That's close, but that's
1,000 charge particles.
it's 1,000 particles at central rapidity.
Yeah.
But
Yeah,
you
it
have
probably-
several
that's what I meant,
units.
like in the acceptance of stuff.
Right. So, but let's say if you were to integrate over, so it's on the order of 8,000 particles. Okay. But that's a good way to think about it, as I'll come to in a second. And this is spread over, do you know how many units of rapidity? It's roughly 6 units of rapidity, right? So it's given by roughly log of square root of S over n nucleon, right, times 2, right? So it's about 6, something like 6 units of rapidity. Now in the LHC, you produce more like 20,000 particles in a single event, and that's stretched between 18 units of rapidity. Did I get that right, Nana? 18 units. Can you see, by the way, can people here see? Sorry, Matt.
I don't need to see
Raju,
it part, that's.
you're also projecting.
Oh, good. Okay.
Raju's in the room, so you can choose
Modern technology.
wherever you can see.
So now, if you just ask yourself, you had this very basic question, right? Is that, so you say you're trying to explain this to your grandmother, as Abe was saying, right? So how many quarks do you have in a gold-gold collision, right? So if you have So each gold nucleus has what, 197 nucleons, right? And so each nucleon has 3 quarks. Right, so this is, that's what, 400, that's, so it's 390, let's say, 393 times 3, right? Sorry?
394.
Yeah, right. 1,000.
Sorry.
1,000.
So it's on the order of 1,200,
Yeah,
right? So you have 1,200 quarks, right, participating, but you have 8,000 particles, okay, that are coming out. So you know that there must be a lot of other dynamics that's going on. And that gets more extreme, right, when you go to the LHC, right? So at the LHC, you have, instead of 197, you have 208. They have the same order of magnitude of the number of quarks that are taking part, valence quarks, right? But you're finding 20,000 particles. And I think you already probably know the answer, right?
Yeah, you have to 8,000 produced particle for one gold.
Yes. Yes, it's a single event. Okay. So you've probably seen these iconic pictures, the star detector and so on, right? But that's not showing the entire acceptance, as someone pointed out. But indeed, or at the LHC, you have these event displays that. Okay, so I guess you know where I'm going, right? Because it's not just the quarks that are participating in this process, it's that there's also the physics of gluons, right? There's half the momentum of the proton itself is carried by gluons, and you know that they're also going to be participating in this process. So essentially the physics of multi-particle production at high energies, physics of glue. Because you see right away at the LHC, you have 1/20th number of particles. We just took all the dynamics to be that of valence degrees of freedom, right? So you know that it must be, and that's again coming back to this physics. Why? Because if you ask yourself again empirically at the LHC, of these particles, what's a typical momentum of the particles in an event? You'll find that it's on the order of 1 GeV. So this is the typical PT per particle, produced particle in the LHC event. While the square root of S, as I mentioned, is 5.5 TeV, right? So this is square root of S. So PT over square root of S is equal to what? It's roughly 2 times 10 to the minus 4. And so that's the value of typical value of X that you're, right? So you see that at the LHC, to understand even the bare systematics of what's going on, the bulk particle production, you have to understand physics at very small values of X in QCD. That's really what I'm going to be talking.
Well, what will be the range of X for?
Yeah. Okay. Well, did Abe or someone talk about
Yeah,
it?
he did.
Okay.
So to check with you.
So I think this itself is instructive, right? So if you say the formula is Q squared over S, right? So it really depends. So S depends on EA or E. So at EA collisions for say gold nuclei, that's the analogy what I'm talking about. That's about 90 GeV. So that's 8100. So 1 GeV squared. So for Q squared of 1 GeV squared, right? You're starting to get to this kind of regime here. Okay. So it's but you of course want to go to. It depends on what Q squared. So the answer depends on what Q squared you prove. Okay, so let me now. So I hope I've convinced you that if I want to understand the bulk systematics of something like heavy ion collision, I need to understand what's happening at smaller values of X, right? That's this region of the diagram here, right? And what I'm going to argue to that things like thermalization and so on really very much depend strongly on our understanding of this physics, as well as some of its interdisciplinary connections. So how much time do I have? When did I start? 3:15, right? Okay, so I have about half an hour. Alexei is going to subtract the time I spent wiping the board for my time, right? Or not included. Okay, so so now I guess in George's Sturman's talk and in other talks, maybe in Ian's talk, you heard about collinear factorization, right? You heard about ideas of collinear factorization. And those set of ideas are really very apropos for this European asymptotics that most of what their lectures were focused on. What I'm going to be talking about is so-called high energy factorization. And that's related to this Raju regime. And this has to do with something which is actually very old. It goes to very early days of just high energy scattering considerations in general. And this is something called the iconal approximation. In fact, it goes back to optics. So these ideas really come from optics. And so the problem I'm going to be talking about is, how do I understand the dynamics of small x? Okay. Now, before I start, let me just mention that you've probably seen these plots, right? Again, of Cartan distributions. As a function of x, right? So this is now going to small x like this. And we learned from Hera that the balanced Cartan distributions have some shape like this, which is peaked around x on the order of 1.7, 1/7 or so. And while you see that the gluon distributions kind of grow extremely rapidly, okay, and they are already, by a factor of x of 0.01 or so, they're a factor of 20 larger than the balanced distribution. So this is so the gluon distributions are very large. Gluons, so the gluon PDFs. And then the C-quark distributions are also quite large. Okay, so these are that of say uplet and beyond. So these are so-called C-quark distributions. They also grow very rapidly. While the valence quark distribution, so these are U valence, E valence, and so on, right? S, and maybe intrinsic charm. So a lot of what we talk about intrinsic charms here. So these are peaked at very large values x, and they become very small and small values. And so as I mentioned, when we try to understand heavy ion collisions, we're really focusing. So how do we think about this picture in terms of physics? So now let's think about something like, okay, so I'm trying to understand this nucleus in heavy ion collisions. And so let's ask, here's my nucleus, right? And it has stuff. So what is the wave function of the nucleus, right? At very high energies. So what does it look like, right? And so that's relevant for Hegelian collisions that I mentioned, right? That's very important. So let's now ask this question in terms of thinking in terms of some probe. So this can be a virtual photon at very high energies that goes into some quark antiquark pair. Okay. And so this has, the quark has a momentum fraction c, it has some coordinate x perp, and the antiquark has coordinate y perp, and this has a momentum fraction 1 minus c of the momentum of the virtual photon. So it has a large momentum in this q minus direction. This is a scattering of the solutions. Now, if I were to think in terms of the parton model, and I'm going to justify this in a second, and my claim is that you can write this nuclear wave function as a collection of different Fock states. So you have 3A quarks, you have a configuration, plus 3A quarks, plus a gluon, plus 10,000 gluons, okay? So you have configuration. So the proton or the nucleus is an intensely quantum mechanical object. It's not a brick. So think about the protons and subatomic particles that you're made up of as just this fluctuating objects that fluctuate into different configurations over time scales. And the reason that you just think about the proton as being, say, 3 quarks is because you're studying the ground state properties of the system for very long times, and that's why you can study that in the lattice, for instance. But on shorter and shorter time scales, in other words, those are probed in higher and higher energy processes, these protons and nuclei can fluctuate in very large configurations. They can carry large amounts of quarks. You know, the quarks don't change, the valence numbers never change. We can have, you know, vacuum valence numbers of gluons just popping up. Okay. And you can have very large numbers and they live for very short times. But if you probe it on those short times, you're going to probe those configurations. And that's what's responsible ultimately for multi-particle production. So how do I understand this from first principles? And you can do this using the ideas of fine energy factorization. And so this is as robust a framework as what is called collinear factorization, and in fact may even have a more general validity. So let's think about this, right? So what do we want to do? We want to compute the S matrix, right? So when you think about scattering, what do? We talk about the S matrix, right? For the scattering. So you say, okay, so think about what is the S matrix? So the S matrix for some final state coming from some initial state can be written as some expectation value, right, of the final state of the whatever object that you're computing for the scattering. And then it's a time-ordered exponential of, I'm going to explain what I mean in a second, from some initial state. Okay, so you have some initial state of the process that may involve the wave function of this guy and this guy, right? And then it goes into some final state that, you know, may involve some other particles as well, right? So, and so what I mean by this, BI, okay, so BI is the, what I would call the QCD Hamiltonian, okay? So did some of the speakers introduce light cone coordinates and light cone, did anyone talk about light cone quantization or?
The coordinates, not
Coordinates, not quantizations. Okay, so you can, okay, I'm not going to talk about light cone quantization either unless people want to ask me about it. Okay, so let me just say that you can write down, this is the Hamiltonian, okay, of QCD, okay, and this is a Hamiltonian in what is sometimes called the interaction picture, where you have fermion fields, you have gauge fields, okay, and think you have some external field. So this is some external field, which is, you know, not directly involved in the state of the object. Okay, so you think in terms of, say, just think about this, for example, as the Hamiltonian of this object here, and think of it as scattering of some classical field, which this nucleus represents. Okay, just for argument's sake. And so it's this Hamiltonian minus the QED Hamiltonian, which is just a function of interaction fields themselves without the external. Now, so what do I mean by this interaction fields, right? Is that it has the following property that if I when this object is defined, so this is a function of x plus, x minus, and x per, right? All the like coordinates. And this is some e3i, e minus, UCD, x plus, psi I of 0, x minus, x per, okay, e minus I, e minus, e. So what the interaction picture tells you is that it takes you from some, say some state at some 0 time. So this is light cone time. So light cone time. Okay. And this is some light cone distance, and this is the transverse coordinates. So the interaction picture is a unitary transformation with the QCD Hamiltonian, right, which takes this field, which are at some fixed static time, to become a dynamical variable. And similarly, there's a similar equation for AI. Similarly, you have a similar thing. So now, let's do the following. Now, is it okay if I erase this part? Let me start over here. I'm just going to keep this. So now let's say, okay, now let me think about these states I or F, right? So this is the objects in my S matrix over there, right? So think of them as objects which are obtained by boosting some static state. This is I naught or F naught. Okay, so these are the initial and final states at the static early times. It's going to be minus infinity, for example. So I can obtain these objects by boosting the state by something, and this is called boost operator. Okay. So what this does, so this object has a property that if you take, for example, the Hamiltonian under boost, it sort of has this property here. So that when omega goes to 0, this object goes to 0 under the action of this K3, right? Similarly, the momentum operator, which is K3 E plus minus I omega K3, goes to E3 omega times E plus. Okay, so the momentum gets boosted by the action of this boost operator in one direction. Okay, so this is the in the P minus direction, if you like. Okay, and then the transverse momentum, T, is invariant under this reduce. And so you can take down, you can write QCD, write down the whole Poincare group. And the Poincare group has to do with the generators of the angular momentum tensor. So that's the boost angular momentum tensor. Okay, so it's a 3-form. And you can write down a set of conserved charges, which are the energy, the momentum, right? And also the angular momentum as well. And so K3 is one of the components of those objects, okay? The angular momentum. And so what K3 does is that it's an action of an operator which takes some wave function and boosts it, okay? And then it tells you how things behave under these boosts. So now let's come back with this understanding to discussing the S matrix again. So let's start back with our S matrix. So I said S of F and I is F time ordered product to the exponential of minus I dx plus vi, right? Now I replace these guys by this. Okay, so I replace F and I, and so I can write this as F naught e to the I omega K3 time or exponential of the stuff here minus I omega I naught. And so now the magic of this boost operator is that if I were to expand out this exponential, right, and take commutators of that with this K3 operator, this has the structure F naught of time ordered exponential of this object now goes into the so it goes right in here. Okay. So you see the trick that I did, right? So I had this boost operator, right? So I start with this wave function. I write this in terms of this boosted elements which are here, right? I just replace this here, that gives me this. But now I can work it out so that these stuffs go into the exponent, okay? And so they have this form here. So the boost operator acts then directly on the interaction Hamiltonian for the scattering. Okay, so you don't want to take my word for it. There's a beautiful, beautiful paper by Bjorkane, Kogan, and Soper. And it's in BizRev D, 1971, where they work out this logic for QED. Very nice. They work out this very beautifully, great detail. And this is actually based on Dave Soper's thesis, and there's an earlier paper just by Kogan and Soper from 1970, which I would also bring to your attention. And so remember, I'm computing the scattering matrix for high energy scattering, right? And so that's why I introduced the boost operator, because I'm interested in high energies. So I take some wave function, right, of this virtual photon, right? And I have a virtual photon going to some state. And I'm saying, how does this evolve under boost, right? So that's what I'm interested in. And then it's going to scatter off some field, which is this field here.
Roger, there's a question.
Yeah. Sorry. So please ask. If you don't mind, I'll clean the board while you're asking.
Okay, just the last line of S matrix, you put it in the exponential, also the exponential of the boost operator, right?
Right. Exactly. So imagine that I were to expand out this b, right? Exponential 1 plus b squared. And then I act on it with all the K3s, and I find that I can re-exponentiate the whole thing in precisely this form where this operator acts on here.
Thank you.
Now you can say, why the hell are you doing this? Okay, but that's the whole point, which I will get to in a second, right? Yeah, sure.
Are we considering an inclusive final state?
Well, so this is kind of a generic final state, right? I haven't really specified whether it's inclusive or exclusive, right? So initial and some final state. And so all I'm right now doing is I'm acting on the wave function. So the problem I'm considering is the scattering of the wave function of this dipole, right? So this virtual photon onto some state, okay, which I treat by this classical view. That's all, okay? I haven't sort of specified anything further. Now, here's where, so that there's magic that appears. Now, this VIs here, so the VIs depend on these interaction fermionic and bosonic fields. And so when I act with this with this boost operator here, what that does is that depends on how these guys act on these psi's. Okay, and so they have a very interesting property that is EPI omega K3, acting on psi I of x plus, x minus, x per is equal to e to the omega over 2 psi I. But what's interesting is in the argument is that it's e to the minus omega x plus e to the omega x minus x per. Okay. And the gauge fields transform differently. Okay. The I omega k3 of ki. Okay. Again, same arguments. So what you now find is that if you take the very high energy limit, right, so where omega goes to infinity, then basically what you find is that this whole object here so bear with me, I'll give you the punchline in a second. Same arguments. So what finds, so this interaction Hamiltonian, right? So which is the difference between the full QCD Hamiltonian. So this is the full Hamiltonian of QCD in the presence of an external field, minus without the external field. Okay, so this is a highly complicated object, right? This is full QCD, okay? In the limit of very high energies, yes.
Yeah, so just in the first transformation,
Sure.
it's like exponent of omega
Right.
times what?
Oh, that's the interaction field, psi I.
And exponent on the left.
Exponent. This is e to the I omega of
Yeah,
the boost operator
After
K3.
after the arrow, like when you have transformed.
Yeah, so this goes, when I act with this transformation, that just goes into omega over 2, omega divided by 2 times psi I. But now the arguments of this function are boosted in this following way.
But what about like dimensions? Like if k has dimension, right? Then I mean,
Well, so-
if you just take exponent of a quantity which is
Well, so okay, so this is just this is from dimensionless quantity, obviously, right? Right, so all this is doing is just transform, it's a unitary transformation of this object here. You're not changing the dimensions, it's exactly the same dimensions. Right, because this is just a number acting on these coordinates. It's a pure number. So what happens is now the limit that omega goes to infinity, that's a boost, right? Because what the boost function does is really increases the momentum by this factor. So when I go to p plus of infinity, that's like increasing omega to infinity. So what it's telling me that this is all that survives of the entire complicated QCD interaction, and all the other corrections are of order e to the minus omega.
I have two questions. First, why does the negative light coordinate transform for the vector?
Negative. Okay, so that's something that depends on details and the properties of the boost operator. Okay, so
Yes, it does transform for the scalar field, but it does transform for the vector.
right. So but because the action of the gauge field operator, I mean, that's the difference between vectors and spinors. Okay? So the action of the boost term contains bilinears of the fermionic fields, and there's bilinears of the gauge fields. They act differently on these objects. That's magic.
The second question is up to now,
Yeah.
We haven't like made any assumptions on our q squared and on our x. So
Yes.
this approach would
Has nothing to do with it so far.
Huh?
Nothing to do with it so far. All I'm
Yeah.
assuming is high energies.
so that same approach would work for like introducing a parton model.
Yes.
Okay.
In fact, this paper is a field theoretic basis of the parton model.
Nice.
And so for the details, this I suggest as an exercise to you. Okay, so please derive these relations. Okay, it's a very interesting exercise. And also, I would look at the formation of Poincare group in the light front and how that transforms and how these operators come. It's deeply interesting. So for those who want to know about the details. But this is if you read this paper, you will really have a deep understanding of not only QED, but and high energy scattering. I'm just the messenger. Okay, so but my point is that I had this very complicated interaction potential, right? And it has all these complicated QED self, QCD self interactions. All that survives is psi dagger psi times A minus. Okay, so it's like a charge density times a gauge field. So it's like the charge J naught times A, right? So that's all that survives, and all these subleading, all the other corrections are subleading. So what does that mean? Okay, so but maybe I'll just give you one more step if you bear with me, and so what I'm going to argue to you is that let me go here. I'm having a serious time issue here, but so let me just say that at the end of the day, when I take the limit of infinite boosts, right, your S matrix, S of F and I, can be written as, okay, at final state of some function, capital F, I, where this object here has this absolutely beautiful structure. It's exponential minus e squared of x squared of some chi of x squared times some rho of x squared. Okay. This only depends on two-dimensional coordinates, transverse coordinates. There's no path ordering involved. Okay. Because the interaction, because of this fact that this boost happens, this takes everything to x plus equal to 0. So the interaction is instantaneous with this field. Okay. And so the only thing that survives is this object here, and this is sometimes what's called the iconal in optics. And formally, so now if I put in color indices in QCD, this can be written as dx plus of A minus its external field of x plus x minus equal to 0, x perp, and rho, this is charge density, is some color matrix dA, dx minus, and then this psi dagger psi, which are functions of 0, x minus. And so this is the famous iconal approximation. So I've taken an enormously complicated process, right? This is full QED or QCD. And I've argued to you that at very high energies, this can be written, scattering can be written entirely in terms of this very simple form, which is really quite remarkable. And I'm going to pictorially show you in a second what that means. And indeed, to further emphasize one of the questions, this is the entire basis of what we think of as a Cartan model. So I haven't even gone to small x yet. So as a consequence of what I just said, you can think of your initial state of the scattering as some unitary evolution of the QCD Hamiltonian, okay, from some time of minus infinity to 0, right? This is where the scattering occurs, of some asymptotic state at minus infinity. And similarly, I can write down the final state as a unitary evolution in reverse from plus infinity to 0 of some asymptotic state at plus infinity. And so remember that I said that S of Fi could be the high energy limit, right, where omega went to infinity, could be written as f of this function f, right, this two-dimensional function with expert, sorry, which then can be written, now if I plug this in as this bare state with unitary evolution of that state from this to 0, f of x per, and from 0 to minus infinity of another bare state. This is the essence of factorization. What this tells you is that you start with some bare state at asymptotically late times, let it evolve all the complexity of QED or QCD. But then the interaction, despite this complexity of the state, its interaction of its constituents with an external object is very simple. It's instantaneous. And then it's separated from its further evolution to, so the past or the future, right? All that complexity then dresses that state over again. So if you absorb all this complexity into some PDF, say, then you can treat this interaction as something that's a short time. So it's really a question of time scales, right? There's a short time process, there's a long time process where the state goes back to itself. So this is kind of really why this is kind of deeply related to the Cartan model. And so further, right, one can write the state I. What is the state I? Which is this u of 0 from minus infinity to 0, state A, can be written as a sum for all intermediate states. So from quantum mechanics, I can write this in terms of all possible intermediate states. So this bare state can evolve. So think of my bare state as the virtual photon, right? So I have a bare state. So let me just make that clear here. So I have a virtual photon. Think of that as my bare state at minus infinity. This state can evolve to virtual photon times quark anti-quark pair, and evolve then to virtual photons times quark anti-quark pair, gluon, okay, plus. So the state can be arbitrarily complex, but it's made of these individual property points.
When you write scattering matrix as the time-ordered exponential of the Lagrangian, and how did that exponential time-ordered part be moved?
Good. I'm glad you asked it, because what happens is that under the boost, you see the time shrinks to 0. So it's really an instantaneous single time. So there's no time ordering left. That's a very important point, because that's why I can write this final result. There's no time ordering left. It's just a simple phase, right? So that's very specific to the very high energy limits. It's like instantaneous interaction, right? At very high energy. And so the basic idea of the Cartan model is that even though the state can be arbitrarily complex, interacting with the nucleus, right, your external potential, the interactions of each of its individual constituents with the nucleus is very simple. They just get rotated by a phase. Okay. So imagine that you have some quark, anti-quark gluon with n gluons coming in, right? A fluctuation. Each of those guys just get rotated by a phase. But then once they get rotated by a phase, then the state can build up into greater complexity, okay, that you measure. But the actual scattering, the information of the scattering is actually very simple, is encoded in these phases.
And the downstream interactions, are they considered like final state interactions after this instant?
Well, you're never, so it depends again on the timescales that you're interested in, right? So if you if you're not looking at very high energies, right? So what the high energies do is actually allow you to resolve states which would otherwise be only excited states in the proton at rest. Okay, so think of the proton at rest as being quarks, right? Most of the time, and then occasionally it's fluctuating into this 3 quarks in a gluon. What happens is when you boost the wave function, those states which are short-lived become longer-lived. Okay, and even more complex states, which are even more short-lived, you'll never see on the lattice, right, would now be resolved. So these are highly, highly excited states in the proton at rest, but they are the proton. So they are the proton as much as the 3 quark state is, right? And so those states start to become resolved, right? And so then you're probing, you're uncovering the veil, which is hiding all these higher excitations, right? So this is another way of understanding deeply the dynamics that binds the proton together. Let me draw another picture to illustrate this point. So imagine you started minus infinity and you had 3 quarks in your proton. Okay, so your proton was 3 valence quarks, tugging along, and had all these very complicated bindings, right, of these gluons which were pressing the proton, right, because they make the proton a bound state. But now let me boost it. So what's happening, right? The physics of time dilation starts to play a role, because what happens is that these guys start to live longer and longer, and they can go into other, so instead of their interactions with each other, right, get highly time dilated, but they kind of start acting like free objects, and they can start to then radiate more and more. So now if I probe this with some high resolution, just 1/2 squared, I'm going to uncover all the dynamics of that was hidden before. So a lot of it, of what we think of as the energy, right, that's binding the proton together, becomes resolved when you probe this at very short distances. So when I say I'm looking at very strong fields at very high energies, that's in essence the physics that I'm uncovering at very high energy. So that's why going to high energies is interesting, fundamentally. So Alexei, how am I doing? Well,
I got mesmerized by your lectures. I didn't check any time.
I'm about halfway through. So I mean, I did all day.
How much time would you like to wrap up today's lecture? Is it a good time to stop?
I don't know, I'll ask Matt what he thinks. I'm just kidding. I'm just
Round
kidding.
so far, the thing that I wanted to add is everything you said, I think, is completely general. Like, this is a purely kinematic statement about the physics of high energies, and none of it is unique to QCD. Like any field theory would behave this way.
Well, so I would no, so it's I would say it's specific to gauge theories. So if you don't have gauge interactions, right, then I think so what I'm saying is that remember that these are properties essentially the Poincare group.
Precisely.
And so the Poincare group in theories with spin 1/2 bosons and spin one bosons and spin 1/2 fermions is qualitatively different from other theories, say scalar theories.
Yes.
Okay, so the transformations in the Poincare group will be qualitatively different, and many of these statements won't be robust. But in QED and in QCD, right, these statements.
So probably gravitons get really sick if you try to boost them like this to high energies, right?
No. It's something, well, it's spin 2, there are peculiarities of spin 2, right? But I think many of the statements actually do also go through in that case.
Right, you're essentially just
So
talking
there's a
about
Ray regime.
Lorentz indices and how they transform as you boost to very high energies. So yeah, very, very general arguments for sure.
So that's why I said high energy factorization in some sense is more general than collinear factorization. Okay? And in fact, collinear factorization implicitly relies on the existence of some kind of.
Sure. Yeah, the separation of timescales is the same. This doesn't yet make any statement about short distance physics dominating anything. That will come.
I did, actually. So this, well, short distance in the sense that, so this is the physics really, you are, I mean, at least in this picture in QED, right? You are really probing things instantaneously in space-time, right? And implicitly, therefore, also at short distances, right? I mean, there's no X minus dependence either.
It tells you whether the X perfect extent is
Exactly.
short.
So that's the non-trivial thing in QCD that one has to further work out, and that's where the collinear factorization assumptions come in. So that's a further refinement of this kind of factorization. That's what the other things.
Will you be posting your notes for us?
Sorry.
Will you be posting your notes for us?
Well, I don't know if it's
Is that okay?
I actually have them all written out, so I could just send a PDF version of this.
We'll attach them to the Indico.
Yeah.
Yes, and the video will go.
Great.
So,
I think it's a good time to.
Yes, I think.
yeah, maybe I think people look tired, so.
Let's thank Raju. I'm gonna leave, yeah, so, anything you wanted to ask it in there, can you do it now? Do we want to wait till discussion time? We have discussion today at 7:30. Are you able to be here?
Unfortunately not, but I can stay tomorrow if people are interested, or I can come earlier, or I can,
I think this works. Here's your chance. If you don't ask, you will never know.
So that's presumably a very stupid one, but anyhow, like, but again about transformation and dimensions, because typically like boost operator is just like plain wave, right? Or not here.
The boost operator is a specific component of the energy momentum, the energy momentum tensor. So this is, so if you think about the angular momentum tensor, so it's the I0 component. So Ki is this component here, and in QCD or QED, it has a structure which is the big side dagger. I think minus. So I'm doing this from memory, but you can check it yourself. But it's a really non-trivial. Think of it as, like the angular momentum transformation or something along those lines, right? So in fact, the nice thing about the light front and the construction of light front wave functions is that the boost operator can use the Hamiltonian. If you quantize a theory in ordinary light phone, let's say there's flat, what you learn in your textbooks, equal time quantization, then in QCD, the action of the Hamiltonian of that state doesn't commute with the action of the boost on that state. So you can actually produce particles by boosting, that state. It's not preserved under boosts, but on the light front, those things are preserved. Yeah.
Maybe another trivial question, but we usually consider the asymptotic states, basically the asymptotic states to be free in some sense, right? So if you go by the factorization statement that we have made, if we start from some free state, it becomes interactive, and then it becomes extremely complicated. Then we have this iconal interaction, and then it becomes simple again, in some sense. So
You're asking where does that come in, right?
Yeah.
So if you look at, for example, think about this as kind of the final state wave function, right? This was my F. Right? Sorry, this was my F, right? So what happens is then as you go from 0 towards infinity, right? All the interactions kind of die away, right? And of course in QCD it's very non-trivial, but in QED,
Yeah.
Actually, you can see in QED, let's think of QED. You don't worry about confinement, right? So in QED, you see that all the interactions die away, right? And actually what you just get are the bare objects. Define some, your final state particles, which are just on shell free particles. You just get free electrons and photons and so on. Final state. So those are your asymptotic states.
I see. So we're not including particles, and basically quarks and so on in our.
Well, so QCD, of course, because of confinement, all of this has to be, because then there's a very non-trivial process QCD we don't understand, whereby then all these quarks and gluons and recombine into hadrons. So the great conceit in perturbative QCD is that we believe that we can treat things with asymptotic states, even though when they strictly aren't, right? But in QED, you can certainly do that, right? Now in QED, there's a subtle complication, which is that there are Coulomb divergences that accompany the asymptotic states, and then there's a problem how to sum those Coulomb divergences. There are soft divergences which then address these states, so that's a separate story. So strictly speaking, the S matrix in ordinary QED is not well defined. I just made a very radical statement. So the S matrix is not a well-defined object in ordinary Q. In fact, the S matrix goes to 0 at very soft momenta. So if you think about the S matrix for scattering, where you emit, so if you say you have 2 electrons scattering, they emit a photon. The process, the S matrix for that process is 0 or soft photon energies. And it's only this modulus squared of the S matrix that's well defined in ordinary QED, and that's what we measure in an experiment. But it's a very funny thing is that we work with an object which is not well defined, but we extract from it something that's well defined. Okay, but then there have been ways to solve that problem, and Vladimir just left. That was my cue. His colleagues Fadeev and Kulish actually they addressed that problem and I believe solved it. But that's a separate interesting story we can discuss. But the S matrix itself is actually strictly not well defined, even in QED. But the modulus square of the S matrix is well, because these divergences cancel at the level of the cross section, and you get something.
So primarily black holes that you're working with, are you assuming that they come from some underlying mass distribution, connected mass distribution?
So okay, since you asked the question, that gives me an excuse to really talk about why these are related. So the process that I'm interested in ultimately, both in QCD and in QED, is a problem that I really didn't get a chance to discuss, is where I think about the scattering of 2 partons, which can be 2 gluons to N gluons, or these can be 2 gravitons. They have the same symbol, N gravitons. And so think about I have 2 guys coming in, and they produce, N things in the final state, okay, very high energy. So in gravity, this would be trans-Planckian scattering. So the square root of S greater than the Planck S, much greater. And so the claim is that at very high energies, these objects, these N guys, they are what form a black hole. Okay, so you can think of a black hole as an overoccupied state of gravitons, which is not C1 over alpha, where alpha is the gravitational self-coupling. And so the techniques that I'm going to talk about tomorrow, which allow us to compute this, can also be applied here. In fact, there's a very beautiful paper by Lev Lepadov from 1981, where he actually wrote down an effective theory for both QCD and gravity, which are actually based on exactly the same framework. So, and a lot of what I'm doing is inspired by that.
This positive note, let's end.